Okay, let's start. Hello, everyone. I'm Christian Duran. I'm going to introduce you to the hardware for trusted execution environments, or TEE, for RISC-V implementations. This was made with collaboration with the University of Electro-Communications (USC), the National Institute of Advanced Industrial Science and Technology (AIST), the Technology Research Association for Secure IoT Edge Application based on RISC-V Open Architecture, or TRASIO. I'm very glad to be here. First of all, the latest presentation, we will introduce first of all our work in a general scope to describe the process of a trusted execution environment. We will describe the implemented hardware to conform to the system from a general perspective in a detailed manner regarding the crypto course and other hardware modules. And finally, we will show results and conclusions about this project. Yeah, that's basically the outline. So let's jump about the introduction of the TE hardware. So the TE hardware system is a hardware generator based on the chisel-based chipyard framework. Chipyard is currently maintained by the USC Berkeley and is a conglomerate of hardware generators and RISC-V cores to create a fully customizable environment. To make it easy, small teams to design, integrate, simulate, and they build custom systems on a chip, or SoC. The request integrated at the rocket chip, the Berkeley auto-order machine boom, and the Series Ariane core. And there is also several kinds of accelerators like the Hacha, the Gemini, and the NVIDIA Deep Learning Accelerator. We build TE hardware, a repository based on chipyard generators. This repository contains the necessary crypto cores and accelerators to execute trusted execution environments, or TEs. You can download it from GitHub in the link shown. It's this link. The current version supports the running of a secure bootloader together with a Linux embedded in a SD card. The software can run in using Accelerators, or also can run in the following FPGA boards. The demonstration includes the elaboration of the root of trust in a zero-state bootloader and the procedure of hashing and signature the Linux to run. So yeah, but first let's talk about trusted execution environment by itself to actually understand what is happening. So for the TE, we use Keystone. That there is a TE framework which includes the interactions with the root of trust in higher privilege levels. An example to use a trusted execution environment is the authentication with on a device and a client server key creation for an asymmetric cipher. So this is the client here. In this environment, we have two participants: the remote PC with also performance station. That is the client here. And the hosts are allocated in the secure environment. The connection can be done using either UR or TCP connections. So Keystone builds a trusted site environment using a chain of trust that is distributed in multiple layers of executive privilege. The chain of trust starts with the root key stored securely inside of the silicon, named the silicon trust. From here, the execution of any procedure must be signed using this root key across the different execution modes, such as the machine mode, the supervisor mode, and finally the user mode, where the host resides. The TE allows the program to create an enclave application on the trusted side from the trusted side of the execution. The explanation of the procedure is as follows. First, the client on the PC makes the connection to the enclave host. This host program cannot be inside of the trusted side, so the enclave application is activated using the Keystone API. This here. This interfaces with the Keystone runtime named area, which runs in supervisor mode. The enclave app then communicates to the secure monitor or SM in machine mode here. That's basically the basic working of this. So in the second step, the verification will create the hash and signature of the enclave application. With this information, the secure application makes an attestation report to enclave the host. then it's sent to the client. This client checks the attestation report for verification. Here you can see the different hashes and signatures of the previous process. The attestation report contains the hash of the signature of the secure monitor and the enclave application together, along with the manufacturer published root key. The previous hashes and signatures come from the procedure of the root of trust. The device.
Could you check the? It's lost the image.
You
thought the video.
Sorry. Can you confirm me if there's still a screen? There's a screen in the presentation right now.
No. Could you maybe release?
I will stop sharing and I will return again in a minute. Is now okay? Can the moderator confirm?
Maybe make the slide a bit.
Yeah. Can you? Okay. I'm going to explain again from here, and maybe the feed it was lost in this session. So, yeah. In this slide, I was explaining about Keystone that builds a trusted site environment using a chain of trust. Yeah. So basically, it starts with the root key that is stored in the silicon itself. So it's trusted from silicon itself. From here, the execution and array procedure must be signed using the root access keys to the different execution modes. So it travels through machine mode again to the supervisor mode and finally the user mode. So the D allows them to actually create applications in the trusted side. That's a version of this. So this is just the procedure that first the client tries to do an attestation. It performs an attestation request, and the claim host will communicate with the Keystone runtime that is named ARI, and everything is done using the Keystone API. So yeah, that's to represent that, and yeah, then in the second step, the actual keystone that is already in the trusted side will generate an attestation report, including the hashes. The hashes are basically here. You can see here that is the secure monitor and the enclave application as well, and the public key. So yeah, that is for resuming that. Sorry for the trouble. I will continue from here. So the previous hashes and signatures come from the procedure of the root of trust. The device key is first verified by the client, which is supposed to be generated using a manufacturer key. But for now, it's stored in the FSVL. The security monitor is verified in the second step, which is signed using the device secret key in the boot procedure. Finally, the enclave application is signed using the secure monitor's key and verified with the public key. Now, the following step is just to establish the communication and exchange the keys for asymmetric cipher. Now, because the client has successfully verified the host, in each environment will create the public secret key pairs, where only the public key is sent to the channel. Now, the communication session is secure and authenticated. In this example, the keys generated are created using SSH. The demo consists of communication streams and send and reply to the verified host. The host will always reply with the number of words the message is sent. That is just a classic demo for this to work. Yeah, so that briefs what is a trusted execution environment. So this it is how the hardware accelerators come inside in this procedure about trusted execution environments. So this memory map here shows the TE cryptography in the proposed system. The upper row is the maybe this is better. Yeah. The upper row is the crypto accelerators memory, and the second row is the main system memory. First, the Linux image with the secure monitor embedded in DDR, depicted in S, is this S here. Is streamed to a SSH hash crypto core. The hash value HS stored locally in the crypto core memory. Then the ED 25519 base point multiplier is used to generate the public secret keys SK and PK. Is here, and it's stored in the write-only memory. This write-only memory, where PK is stored, while SK is stored in the secure memory, the public key is just stored in regular memory. The final verification is performed by signing using the curve 25519 calculations. So we just rehash this image again and use it to actually sign the generate a certificate using 25519 algorithms. Okay. So let's talk about the actual hardware that is integrated in this system. So this figure here depicts the implemented system on a chip architecture. We implemented a coreplex of several RISC-V processors supporting integer, multiplication, and floating point operations, which are necessary for extensions for Linux to be compatible. These processors can be either the Rocket core or the Boom core. Right now, the Boom version 2 is implemented in the master branch of the repository. So the version 3 is still not used actively due to its stability problems. But the same implementation also exists for the version 3. So that's for acceleration. The coreplex contains several implementation of the tiling bus to access the system, peripheral memory buses. Attached to the peripheral bus, the system contains regular input and output devices like the GPIO, the multimedia card controller, the UART, the USB, and the PCIe. It also contains memory devices for programs and data such as the mass ROM, the SPI ROM, the DDR controller. The crypto accelerators are also attached to the peripheral bus, whose configuration and data I/O are memory mapped using register routers. So the following table illustrates the configurability of the hardware generator. Right now, we support 3 FPGAs, so the VC707, the Silent VC707, and the Altera the TE4 and TR4. You can set the ease extensions and the word size here, and also you can configure the hybrid connections of the processor. So either if you want two Rocket cores or 2 Boom cores, or if you want just a hybrid or a Rocket Boom where the Rocket is the first core, that is also possible. So another features, including the PCIe and the DDR clock and the boot sequence, are also configurable using parameters as well. So here we illustrate how the different processor configuration are displayed using Linux. So each one of this is a hardware compilation running Linux, and this is acknowledged by the Linux itself. You can see that the processor architecture inside the CPU changes whenever I build a different hybrid implementation for the Rocket and the Boom processors. There is a configuration and the word size also reflected as well. And finally, this table reflects the logic utilization in the VC707 FPGA with the different processor configurations. The biggest utilization is the 2 Boom core, located here. Which practically uses over 50% of the overall logic utilization of the FPGA. The hybrid configurations with Boom and Rocket have roughly 40%, and the smallest hardware is 2 rockets. That is roughly 30% of the FPGA. You can achieve even smaller configuration using 2 rockets in 32-bit mode, supporting only IMIC extensions. That is roughly 20% of the overall FPGA. So let's talk about the crypto core accelerators themselves. So we included these crypto cores. The list are the SHA-3, the accelerator for hashing, the ED25519 accelerator for generating keys and signatures, the AES for encryption. We support AES 128.56. And a PRG that is going to act as a random number generator. The crypto cores can be bought from the peripheral bus to be implemented as a custom instruction using our ROCC. The AES can support 128, 166. ED25519 contains 2 separate accelerators, namely the ED25519 multiplicator and the ED25519 signature for pair key generation and certificate verification respectively. PRG is done using just linear feedback shift registers, but we developed the PRG for a future use for a real for a true random generator, and it's using the ARM trust register model for the RNG. That for support compatibility at least. This table reflects the logic utilization of the crypto cores. The biggest core implemented here is the ED25519 sign accelerator, which contains most of the logic for arithmetic multipliers. The base point multiplier also contains arithmetic multipliers, but the resources are bigger in memories, where the secure keys are stored and actually operated. The SHA-3 and the AES are purely logic implementations, so they are smaller. In ASIC, the area of occupation is consistent according to the FPGA. ED25519 is still the biggest because of the random utilization. The other 3 cores are purely logic implementation because they only use like multiplications or just bit operations over the stream. And this execution environment was tested on the system using pure software and hardware accelerator implementations. The process to authenticate the payload mostly uses the SHA-3's hashing, even the ED25519K pair and signing as an additional calculation process. As we can see here, the hardware solution decreased about 2.5 decades of execution compared to the pure software approach. And here we also show the throughput of the verification operation using SHA-3. The acceleration can output up to 30 megabytes per second. This about 270 times faster than using pure software. The other hardware modules also included in this is the spy room that hosts a full water external device. With this device, it's possible to do debugging faster because you can just upload multiple binaries. The system sets the RISC vector actually in the address 10,000 or the 20 million address. I will send it in the 2 million address, recite the zero state bootloader or CSBL, where the actual root trust is started. In the case of disabling this QSPI, the boot room will contain the CSBL. This is the scenario for release hardware, where the authentication process needs to be secure and the boot room needs to be not writable at all. But for debugging, we recommend activating the QSPI, where the boot room is a simple snippet to jump to the 20 million address, and you can host the CSBL in the QSPI. The other device is the main memory controller, which is externally synchronized to match the DDR controller. In this case, we capturing the past and use a different clock domain for external bus control. The intention is to have flexibility at the moment of using external IP for the main memory. Usually, the main controller handles a different clock and bus size. Particularly in your case, the IP can use a 64-bit X4 interface for the BC707 and 32-bit Avalon bus for the Astera boards. So it's different in each one of the implementations. So talking about chips results, so the platform we implemented the platform in a 100 nanometer process, from 100 nanometer process, 180 nanometer process. The first version contains just a 4-core rocket chip platform where the crypto cores are not yet not included. The size of the die is 4.5 times 7 millimeters. It draws about 380 milliwatts of the maximum frequency of 92 megahertz. So another version of the platform includes 2 rockets and was also implemented in ROM 180. This includes the SSH3, the AS, the ED25519, the QSPI, and the USB 1.1, bringing the necessary devices for performing acceleration for the trusted execution environments. The size of the die is 4.5 times 4.5 millimeters and draws 706 milliwatts at the maximum frequency of 98 megahertz. This photo of the TE hardware demo, interfacing the chip with the FPGA for the DDR controller. Both of the chips do not actually have a DDR controller built inside, so we decided to externalize the main memory, the main memory tiling port, and with this we connect the PCB to a tiling port inside of the FPGA, which contains the DDR controller. Finally, to conclude this presentation, here are the final remarks. In this presentation, we show a hardware generator for trusted execution environments. This hardware implements several crypto cores that include SSH3, ED25519, AES, as well as several peripherals for input, output, and memories. This hardware generator is configurable according to the needs of the final applications. It's also capable of choosing the RISC-V cores to be used and the ISA options. We tested the design with several FPGAs and it also implemented in 100 nanometer technology. We demonstrated also that the time of execution for the TE tasks using hardware accelerators dropped significantly compared to pure software implementations. We want to also acknowledge the new energy and industrial technology development organization, NIDO. The presented work is based on results commissioned by it. So yeah, that's all for my presentation. Again, thank you very much for having me here. I open to questions right now.
Thank you for your presentation. Yeah.
Christian, do you want to just actually on screen, like that, change the screen mode back to your face?
Like this is okay? Yeah, I hear.
Okay, thank you.
No, thanks to you to actually having me here.
So, there are plans for supporting another RISC-V processor as well.
Sorry again.
Okay.
あ、音が。
Yes, sorry, I didn't understand. It was a question?
Okay, go ahead. One more time.
Okay. Now,
Yes.
can you list? Okay. Okay. And the first question. You stated that there is support for the rocket chip and boom processor. And there are plans for supporting another RISC-V processor as well.
Okay, right now we only support the rocket chip and the boom processors. In theory, it's also possible to include also the Ariane core because it's part of the cores that are supported by the chip year environment. But right now, I think it's not possible for the Ariane to actually support the TE as they don't have. Maybe they don't have. I am not actually completely sure that they have a PMP. That is the actual requirement for the TE to work. Right now, in this moment, we are including the IWES processor from low risk. That is for including the Open Titan secure rotor trust into this system. So in a near future, this project will be able capable of supporting the IBEX core as well. That also supports the secure environments. That's pretty much it.
Okay. Okay. Thank you. And second question, okay? And as for the silicon root of trust, what do you think is the future plan to include this future inside of the TT hardware?
Future. Well, right now, I stated in the presentation that the actual silicon of Lotus Trust is still not totally fully completed inside of, for example, this hardware corplex. The reason of that is that most of the it needs to be silicon dependent. So usually it depends of the IP that is actually that actually handles the actual root of trust of the system. So you can see it like a Mac address that is totally embedded in the silicon, and it's only going to be accessible by the highest of the of the execution modes. With this, we can with this, and also with a true random number generator, it's possible to push forward more the trusted execution environments inside of RISC-V. So the plan right now is to actually just give a little more of it, or insight of what will be the rough trust, and afterwards just having the actual silicon, maybe in a posterior run to actually have the fully rough trust completely enabled in RISC-V systems. So yeah, that is for the foreseeable future, approximately maybe up to next year.
Okay, thank you. And last question. This system seems a very good option for high-end processing solution, but regarding the Internet of Things, there is a way to perform build of this hardware for microcontroller scale hardware.
Well, I said it before that we are including the IBEX processor. Actually, the IBEX processor is more like for making the the secure the secure execution environments to the IoT kind of environments. Sorry for the redundancies, but yes, the system in theory, this hardware generator is capable to downgrade the whole system to just support microcontrolling implementations. So maybe by just configuring the buses implemented, and also making not using the boom right now, but maybe the rocket chip with a small configuration, but supporting the PMP. It's still possible to have the TE hardware to be supported in a minor scale. Yeah, that's why I thought that. But right now it's just for high end, and maybe when we have the open Titan part of the hardware also implemented in the system, we will also support the parts for IoT and low power implementations.
Okay, thank you. Thank you for your presentation, Mr. Duran.
Thank you very much.
Thank you very much.